Hello, everyone. I'm Juanjo Aguilar from the University of Zaragoza. I'm going to present the PhD of Vignesh Sampath, that is not here. So, he's from India. Before entering the project, he was working in Tata Research Center, working in computer vision, deep neural networks, machine learning, and so on. And he started the PhD in October 2019. He was working in Tekniker. It's a technical center in the Basque Country, and we supervise this PhD from Tekniker and from the University of Zaragoza, but focused in an industrial problem in Eureka. He finished in 2023 in the PhD, and he started working in Tekniker, but now is in Chicago, working in the Argonne National Laboratory and working in this kind of field. So it was very difficult to come here today, and so I'm trying to summarize the PhD. The PhD is working is about deep learning algorithms in Industry 4.0 in the application of surface defect inspection for quality control. Okay, the industrial problem is in Eureka they are manufacturing fasteners that in that manufacturing there is involved cold and hot forging, thread forming, heat treatments, surface finishing, and these kind of products are important. They need to load a lot of different kind of loads. So it's important that these fasteners are fasteners could lead to the failure of the assembly or the structure, and we have to avoid that. And then the last part of the manufacturing processes is an inspection. These kind of products are inspected using magnetic particle inspection. This is a manual process and not quite easy, so we need qualified operators to do that. We used to use suspended ferromagnetic particles, and using ultraviolet light, you can see small cracks in the surface and even near the surface. So the objective of this PhD was to make that in an automatic way using computer vision and also deep learning techniques. The question was how we can automatically distinguish bad parts from good parts in a way reliable, easy, quick, and economic. So the three main objectives of this PhD are related with image acquisition system. After that, working with this data, and after that, developing the deep learning module. So I'm going to describe these three first objectives that I think are the most important. Well, there are different kind of fasteners, and there are a lot of factors that influence the magnetic particle inspection. The concentration of the particles, the camera position, the lighting conditions, also the defects that are different, and also are different fasteners, and also the surface finish is different depending on the treatment process. And we need a visual system, a camera, or some cameras that should be able to capture all these variations. So this is the final setup he developed. Here is the part. The part has to rotate, and there is a magnetic suspension spray, and here are the cameras. There are two cameras or line scan cameras. These are some examples of these images captured with the system, the framed cameras or the line scan cameras. These are accurate enough, but using line scan cameras, you can have much more accuracy, 4,000 by 4 or 8,000 pixels in the resolution. So with these both technologies, one of the objectives was to have a data set with enough information about the fasteners and the defects on the surface. Using this data, we have to look at this and try to improve, because normally fasteners has not defects. Only some of them have defects, and then the defects also are different kind of defects, and some of them we have a lot of them, but some of this kind of defects are very rare, so we have only some images of them. Then we need to use some techniques to expand the size and diversity of this training dataset. The question is, using this dataset, we have to develop and to train a model that should be invariant to this kind of factors. So there are a lot of factors that depends on, for example, the camera or the part position, the illumination, the defect position, shape, size, and then we have to develop some image augmentation techniques. Some of them use the position invariance. Some of them use the camera parameters invariance, changing some of them. And the third one is the most powerful technique, is to develop a tool in order to create a synthetic image in order to have enough information to train the model. This technique uses GAN, Generative Adversarial Neural Network. There are two steps. The first step is the generation. From a mask, it is necessary to develop a virtual image of the defects very similar to the original one. And then to train this step, it's necessary to develop the discriminator. This is the second step in order to know if this image is real or not. So the question is to improve this generator in order to fool the discriminator, no? And in that way, we can generate a lot of digital or synthetic images with a lot of different kind of defects, very similar to the real ones, without having these real images. And then the third step is to develop the model using deep learning techniques. Defects are very different, and also there are a lot of noise in the industry, in the reality, and this is not very easy to detect and to classify this kind of defects. So he was working a lot trying to improve different kind of deep learning models that are in the state of the art. And at the end, he developed one of them. This is the deep learning tool that he developed. And we make a benchmarking, comparing it with very well-known proposals. And at the end, he obtained a good accuracy, precision, better than the others. So for that problem, this deep learning tool reached a very good performance. Well, in the future, it's important trying to certify this system. This technique is certified, so it's accepted to inspect this kind of products. But in the future, we want to change that and its next task is to certify this new procedure. Also, try to make this more versatile and also to be more adaptable to new environments. Well, finishing, there are three main contributions: the dataset, the generator network, and also the deep learning model. Of course, this doctoral thesis had the industrial mention, and he published a lot of papers, some of them with a lot of citations. And this is the last day. This is the supervisor from Tekniker, me from the University of Zaragoza, some members of the PhD committee, and Vignesh, that now is continue working in that field and in a very good laboratory, one of the best in the world, I think. So thank you, Vignesh, for the work. Okay, thank you.